Welcome to The Explainer, where we break down the big stuff. And today, we're going really small to look at the huge, invisible forces that hold, well, everything together. We're talking about the secret social lives of atoms and the bonds they form.
I mean, think about it. The salt on your fries, the water in your glass, it's all just atoms connecting with other atoms. But how do they do it? What are the rules of the game? Let's dive in and find out.
All right, so to really get this, you have to think about atoms like tiny little individuals. And they all want one thing above all else: stability. They're basically just trying to find their happy place.
And that happy place, that ultimate goal, is all about something called the octet rule. It's the golden rule of chemistry. The idea is that most atoms are desperate to get 8 electrons in their outer shell. Why 8? Well, that's what the noble gases have, and they are the most stable, unreactive elements out there. They're the cool kids. So this drive to get to 8 electrons, it's the motivation for pretty much everything we're about to talk about.
Okay, check this out. Here we have 2 chlorine atoms. Each one starts with 7 electrons in its outer shell. So close, but not quite at that magic number of 8. They're unstable. So what do? They make a deal. They each share one of their electrons with the other, creating this shared pair right in the middle. Now, each atom gets to pretend it has 8, and poof, they're both stable. That's a covalent bond in a nutshell. But, it's not always that simple. Sharing isn't always equal. It all comes down to a constant, invisible tug of war for those electrons. And the name of this game? It's called electronegativity. Electronegativity is just a fancy word for an atom's pulling power. You can literally think of it as how strong an atom is in this electron tug-of-war. Some atoms are like Olympic weightlifters, yanking electrons toward themselves. And others, well, they're not so strong. And this difference in pulling power, it is absolutely crucial. It determines everything. And here's the cheat sheet. This periodic table shows you that power ranking. See the trend? As you go from left to right and from bottom to top, that pulling power, that electronegativity, just gets stronger and stronger. And up there in the top right corner, you've got fluorine. It is the undisputed champion of this tug of war. Meanwhile, way down on the bottom left, you have elements like francium. They're going to lose that fight almost every time.
So this difference in pulling power is what creates all the different kinds of bonds. It's not just a theoretical number. It leads to 3 totally different outcomes when atoms meet. Let's break them down. Okay, outcome number 1. This is what happens when the matchup is completely unfair. We're talking about a huge difference in strength. It's not a tug-of-war anymore. It's straight-up theft. One atom is so strong, it just rips the electron away from the other one. We call this an ionic bond. And it all goes down in 3 quick steps. First, the transfer. The strong atom grabs the electron. Second, you get ions. The atom that lost an electron becomes positive, and the one that gained it becomes negative. And third, attraction. Positive and negative are drawn to each other like magnets, and that powerful force is the ionic bond. And the classic example of this is just regular old table salt. You've got chlorine, which is super electronegative, and sodium, which is not. So chlorine just snatches that outer electron from sodium. Now you have a positive sodium ion and a negative chloride ion, and bam, they snap together to form the salt crystals you put on your dinner.
All right, so what happens when the atoms are more evenly matched in that tug-of-war? Well, then they have to share. But sharing comes in 2 flavors. You can have pure covalent sharing, where it's perfectly equal. Or you can have polar covalent sharing, where it's kind of lopsided. It all just depends on that difference in electronegativity. Let's look at 2 great examples. On the left, you've got carbon dioxide, CO2. The 2 oxygens are pulling on the carbon in opposite directions, with equal force. It's a perfect stalemate, totally balanced, so no charge. But now look at water on the right. That powerful oxygen atom is hogging the electrons from the 2 hydrogens, pulling them closer. This creates a little molecular magnet with a slightly negative end near the oxygen and slightly positive ends near the hydrogens. And this polarity is, well, it's a huge deal. Okay, last one, metallic bonds. This one is totally different. It happens in, you guessed it, metals. Instead of fighting one-on-one, all the metal atoms decide to just pool their resources. They throw their outer electrons into this big community pool that just flows freely among all the atoms. It's like a sea of electrons. And that freedom of movement, that's exactly why metals are so good at conducting electricity and heat.
So here's where it gets really cool. These bonds aren't just invisible glue. They actually give molecules a specific three-dimensional shape. This isn't random, it's all about how those electrons are arranged. And the rule that governs this is called VSEPR theory. Now, that sounds complicated, but the idea is incredibly simple. It just says that electron pairs, because they're all negatively charged, repel each other. They want to get as far apart as possible. Think of it as the ultimate rule of personal space, but for electrons. So let's see how this plays out. Imagine you've got a central atom, and it's bonded to two other things. How do those two groups get as far away from each other as possible? Well, they go to opposite sides, forming a perfectly straight line. That's a 180-degree angle. We call that a linear shape. Simple, right?
Okay, now what if we have three groups? Well, they can't make a straight line. The best they can do is spread out into a flat triangle, kind of like a peace sign. Each one is 120 degrees away from the others. That's trigonal planar.
And with four groups, now things have to get three-dimensional. To really get away from each other, they form this 3D pyramid shape called a tetrahedron. And this shape is everywhere. It's a cornerstone of organic chemistry and even biology. It's fundamental to so many molecules, including the ones inside our own bodies.
Okay, so who cares, right? A line, a triangle, a pyramid. Why does any of this molecular shape stuff actually matter? Well, let's bring it all together and look at probably the most important substance on our planet, water. So if you draw water on a piece of paper, you'd probably just draw it as a straight line. But in reality, thanks to VSEPR theory, we know that's wrong. See, the oxygen in the middle actually has four groups of electrons pushing each other away. Two are bonded to hydrogens, but two are just lone pairs hanging out. They all push each other apart into that 3D tetrahedral arrangement. But since we only see the atoms, the molecule itself has this characteristic bent shape.
And that simple bend, that is water's superpower. Seriously, because it's bent, the powerful pull from the oxygen atom isn't canceled out. It creates that polarity we talked about, that molecular magnet. And that polarity is why water is such an amazing solvent, why it can dissolve things like salt. It's why water molecules stick together to form a surface. And it's even the reason ice floats, which is critical for life in our oceans and lakes. All of that comes from one simple.
So think about this. If water molecules weren't bent, if they were just straight lines, would life on Earth even be possible? The next time you see a glass of water, just remember the invisible tug of war and the simple geometry that makes our entire world work. It's pretty amazing when you think about it.